Welcome back. This is an Aleks training video on deducing information about reaction mechanisms from a reaction energy diagram. Reaction energy diagram, remember, is the energy it goes that you see that it's going to need to invest to go from reactants to products, and the energy that's stored in the bonds of the reactants as opposed to the bonds stored in the products. So you've got a more of a complicated looking diagram here in this question than we've had in the past. Instead of one hump, I've got two humps, and instead of two lines, I've got three lines. So this is something a little more complicated. You're going to see that the left is the same. It's always going to be the reactants, and there's a certain amount of energy stored in the bonds of those reactants. And so the energy that this has, the potential energy that that molecule has, is based upon the energy stored in the bonds of those reactants. At the end, you'll always have products. Products are going to be what you make in a chemical reaction, and the bonds in those molecules also have energy stored. So in the case of this guy, where the products are higher than the reactants, this would be endothermic. Energy is actually coming in from the environment, stored in the bonds, and so you're raising in energy as the reaction occurs. In between the reactants and the products, in a complicated mechanism like this, you're going to have a middle line that's energetically stable for a short time. This could be a millionth of a second, or it could be something longer, but you're actually going to make something. You're not going to have any at the end, but you're going to make a molecule called an intermediate. And so this here is the intermediate product. And then all those intermediates are used in the second reaction. So there's really just two reactions. You've got a reaction here where reactants are making something, and then a second reaction taking place where the intermediates that were made by the reactants are then themselves used as reactants to make the products. When you look at the entire reaction, it just looks like you put some stuff in the test tube, and at the end you end up with something new, but you did have some intermediate and some. So this is what's happening in your body. Your body are not just very simple elementary type of reactions. These are very complicated reactions, sometimes many, many steps, and so you have some of these intermediates. And so one of the questions they're asking is about these intermediates. On the right, I've given you some definitions that may help you answer this question. The first is called the transition state or activated complex. If you remember what I said about the Legos, if reactants are Legos put together in certain configurations and products are the same Legos put together in different configurations, then the activated complex is this idea that there must be a moment when the bonds are broken but new bonds are not formed yet. That's called a transition state. Imagine moving Legos being pulled away and kind of floating in space and then redirecting and coming back together. That transition state is that momentary idea where you're going to end up with kind of nothing. Only just atoms is the only thing, where bonds have been broken but new bonds have not formed. So a transition state is, like I said, it's an idea, never seen because it's probably instantaneous, but the idea is before bonds can be made in the products, bonds have to be broken in the reactants. So every time you make something, you're going to have a transition state. So in the case here where we have intermediates, this would be there's a transition state probably right here at the high point of the energy from here to here. So there would be a transition state here, and then there's a second transition state here, probably in this region. So it says here the particular arrangement of reactant and product molecules at the point of maximum energy in the rate determining step of a reaction. Okay. The second idea here is an elementary reaction, which is like a single step. Okay, if you can go from reactants to products in one shot, that's called an elementary reaction. And then the process in a chemical reaction that occurs in a single step, an overall chemical reaction consists of one or more elementary steps. So if this is making one thing, that would be an elementary reaction. if this is taking the intermediates and making something, this is an elementary step. And then the overall equation in this guy, the overall reaction, would be the combination of these two elementary steps. So they're going to ask you essentially, is it an elementary reaction? Can it happen once? Is there one shot or is there more than one shot? That's what they're asking. And then the rate determining step is the slowest elementary step in a reaction mechanism. So again, if I've got this guy, I've got essentially one reaction here, okay, and then I have a second reaction here. So which one is the rate determining step? Okay, so for instance, if I'm trying to get from Milton to Charleston, and it takes me 30 minutes, what's my, and 30 minutes to drive, what's my rate determining step? It's probably the road work between Milton and Hurricane that drives everybody crazy. I can get to Charleston based upon how slow that traffic is, because if all the rest of it's easy, I know what the speed limit is, I can determine the rate. So the rate determining step is which one's going to slow you down the most. So that's easy when you look at a mechanism like this where you have a diagram. You're looking for the activation energy, the energy that's going from reactants to first products. How much energy is that? Well, the bigger that energy, the slower that step, the less likely it is to happen. So which of these two, going from here or going from here, which of these two is your higher? That's what they're asking. Which one is more energy? Whichever one of these is more energy, that will be the least likely to happen and the slowest of the slow steps. Okay, my guess is it would be number 2. This is higher in energy, so this would be your rate determining step. This one is easier in energy. You're going to have more likely for it to happen. And this is slower. It's less likely to happen. Okay, so let's put all this together and answer the questions. Number 1 says, does this reaction release or absorb energy? Well, do the products have more energy than the reactants? Yes. That meant it absorbed energy. It came from nowhere. It came from the environment. Okay, so this would be absorb. What about the second question? It says, how many transition states are there? Well, remember transition states. How many times do the molecules break apart and reform? Well, it's at the high point of the energy again, which would be here and here. So I see 2 transition states in this example. You're looking for humps. Okay, so there would be 2 transition states. Could this be an elementary reaction? In this case, it can't, because in this case, I've got 2 transition states. That means I've got 2 making products. I've got a products being made here and then a products being made here. So it can't happen in a single step. This would have to have 2 steps. So this would be no, you cannot answer this one, or you couldn't do this one in a single step. If you said this reaction could not be elementary, how many steps are in this mechanism? Okay, well, how many activation energies do you see? I see 2. Okay, so there would have to be 2 steps in this mechanism. And then if you said this reaction could not be elementary, enter the number of step in the mechanism, which is the rate determining. All right, well, which one is slower? Which one it requires more energy? Number 1 or number 2? It would be number 2. Number 2 again, because it has the higher activation energy and it's slower to happen. Okay, I hope this is making some sense to you.